Okay, we're going to move into talking about gases, one of the phases of matter. And let me just share. So the reason we're going to start talking about gases, we'll talk about gases, solids, and liquids, which are the three most common phases of matter. Remember, there was also plasma, but on Earth, that's not a very important phase. But in this chapter, you'll see a lot of application of what we've already covered. So we'll think about molecular structure. We'll think about intermolecular interactions. We'll think about stoichiometry. So these chapters on gases, liquids, and solids will incorporate a lot of other things we've already done. So it should be helpful in the sense of starting to review things. So we have gas pressure. So basically, we want to think about the fact that the state of a gas can be described by the pressure, the volume, the amount of the substance, and the temperature. And so we start out thinking we have to be able to measure all of those. That's why they list gas pressure first, because that's probably something you haven't had a lot of experience measuring. So all of those come together, those variables, into an equation that's called the ideal gas law. It's an equation of state. If you know those relationships, you know what state your gas is in. We'll go on to talk about stoichiometry. So in that section, we really won't do anything new. We'll just go back and think about stoichiometry, where we tended to think about mixing things, reactants, for example, in gram ratios. But here, maybe we'll use volume ratios because we're dealing with gases. We'll talk about effusion and diffusion of gases, the kinetic molecular theory, and then something about gases when they're not behaving as the ideal gas law would make you think. So I think the most important thing to think about before we really get into this is what is the definition of a gas? So a gas is a phase that fills the entire container. So if you have a flask and it has some nitrogen gas in it, it's going to fill that whole container. It's not going to sit at the bottom like a liquid would or a solid. So by definition, a gas fills the entire container that it occupies. So this was one of the reasons why gases were one of the first phases to be understood, is because people at this time were trying to figure out how you could use balloons as transportation. It was quite a while ago, but if you can get the air inside of the balloon to be less dense than the air outside of it, it will rise. And so you could use that as transportation. And so we'll see in the ideal gas law that there's a relationship between temperature and density. And so if you raise the temperature of the gas inside the balloon with a flame, then you're going to be able to use that balloon for transportation. So one of the things we need to be able to measure is pressure, because pressure is a very important property of gases. So first we're going to define it, and then we're going to convert between different units. We're going to look at how you measure it, and then we're going to calculate it from those measurements. So when we talk about gases, and especially if you're thinking about atmospheric chemistry or environmental situations in our atmosphere, air is probably the best example of a gas that you interact with every day. So let me move my pictures. So that means that it's been studied for a long time. The Greeks considered air to be one of the fundamental elements of nature, along with earth, water, and fire. So that was a long time ago. And in 18th century, air was determined to actually be a mixture of different gases. So lots of people were studying air at that time. Air in the news. So air in the news, these are only two small examples, actually, compared to all of the air pollution, hurricanes, which involve air movement, all of those different things. But depletion of the ozone in the stratosphere, which meant we were depleting the molecule that protects us from ultraviolet radiation, and then carbon dioxide and global warming. Those are two things they haven't been in the news, in my opinion, as much as they should be lately. I saw a small headline recently that we had thought that we had solved the problem of ozone depletion by getting rid of CFCs, which caused that ozone to break down. But in reality, they're finding that the ozone hole is still alive and well and still continuing to deplete the ozone. So hopefully we'll hear more in the news about that. And of course, carbon dioxide and global warming, we hear all sorts of examples of its impact on us, from sea level rise to more hurricanes to more fires. So both of these could be in the news, could be the entire news every night, in my opinion. But then you should also add to this just pollution of the air. So adding sulfur dioxide from burning coal, or nitrogen oxide from burning fuels in your car. So you have all of these issues. You have mercury also as a result of burning coal. It's a toxin in a lot of coal samples. So just there's so many reasons why the air in which we interact is really an important thing in the news. So the atmosphere above us exerts a large pressure on objects at the surface of the Earth. So we have gravity holding all of that air in. And so mass times acceleration due to gravity is force, and pressure is force per unit area. So when we look at all of that air with a mass and the acceleration due to gravity, that force pushing on the surface of the Earth per unit area would be called a pressure. So it's roughly equal to the weight of a bowling ball pressing on an area the size of a human thumbnail, which is really interesting. I mean, that sounds like that would just plain hurt, but we have evolved to understand or to recognize that as normal, so it doesn't impact you. If you put a bowling ball on your thumb, then you would have twice that atmospheric pressure, and then you would definitely feel it. So pressure is defined, as I just said, as the force exerted on a given area. So force from gravity holding something down is that mass times the acceleration due to gravity. So gas pressure is a result of the force exerted by gas molecules colliding with the surface of objects. So if you have a container, or if you have that balloon they were trying to use for transportation, inside the gas molecules are flying around and they have energy. And so they're hitting the surface of that container, and they have force when they hit the surface. So the pressure of the gas is that force of those collisions per unit area of the surface of the container. So in English units, we would often use pressure in units of pounds per square inch, but we're going to see a lot of different units if you're talking about doing science. Oftentimes, what would you call it? The common units aren't as useful. So a mercury barometer is a device used to measure the atmospheric pressure. So let's, soon we'll see how that works. So this is just an example of that idea that it's not just force. Pressure isn't just force, it's force per unit area. So when you look at this picture, you would think that the elephant has more pressure on the earth, but it's actually the ice skater, because the ice skater has her weight all on a very, very, very thin blade for her skate. And so the force, or the mass, is smaller for her than for the elephant. But because that unit area is so much smaller, it makes the pressure much larger for the ice skater. So millimeters of mercury is a common unit for pressure, and we'll see in just a second why that's true. Probably the most common unit of gas pressure is atmospheric pressure, or pressure of an atmosphere. 1 atmosphere is the normal atmospheric pressure. 1 atmosphere equals 760 millimeters of mercury. So it's essentially, you want to think about the pressure that you find at sea level, because as you go up, pressure goes down. So 1 atmosphere is about the pressure at sea level. So these are just some units. SI units of pressure is the Pascal. So a Pascal is defined as the pressure exerted by 1 millimeter thin film of water on the surface beneath it. So that's the pressure created by that thin amount of water. So a Pascal is a really small unit of pressure. So a related unit of pressure is the bar, and 1 bar is 105 pascals. So when you think about a Pascal, it's a pretty small unit of pressure. When you convert pressure, there'll be lots of unit conversions in your book, but here's just one of them. There's a table in your book. A bar is about an atmosphere. An atmosphere is 760 millimeters of mercury, which is equal to 760 torr, which is just another unit named after a man named Torr. And then we have the pounds per square inch, PSI, which is often used like if you're putting air in your tire, you'd usually measure that with a gauge that would be in PSIs. So if you relate a PSI to a kilopascal, you have 14.7 pounds per square inch is equal to 101.3 kilopascals. So if we want to measure pressure, this is probably, so when we think about the other properties of gases, you've measured volume, you've measured number of moles, you've measured temperature, but you probably haven't measured pressure. So a barometer measures pressure in terms of the height of a column of liquid mercury. So the atmosphere exerts a force on that column of mercury, causing it to rise. And then you can look at that rise when it stops based on the fact that that column is being pushed down by the force of gravity, mass times acceleration. So commonly the pressure of the atmosphere at sea level pushes the column of mercury about 760 millimeters high. So this is a picture of that barometer. So yeah, and it's comparing, so a barometer usually has mercury as the liquid. So if you think about it, mercury has a density of about 13 grams per milliliter, whereas water has a density of about 1 gram per milliliter. So when you think about that, the same volume of mercury will be much, much heavier. Therefore, the mass times acceleration of that being pushed up against gravity is going to be much greater for a smaller volume than the water. So that's the same thing as saying the atmosphere will push mercury up not very far, whereas this is showing you that it's going to push water up very high. So in each of these cases, you have a tube that's empty, and you place it upside down with it sealed at the top into the tub of mercury or water. And then atmospheric pressure, shown in this little blue arrow, is pushing down on that mercury in the container, and therefore pushing mercury up the tube against gravity. And so how high that column goes is a function of the mass times acceleration, pushing it back down. So when you look at this, atmospheric pressure is going to push mercury 760 millimeters, where it's going to push water 10,330 milliliters, or 33 feet. So pressure varies with the height of the column of air above, and we don't notice atmospheric pressure, but we do notice changes in the atmospheric pressure. So the force, so if we want to measure the pressure of a gas that's in a flask, we can measure it relative to atmospheric pressure. And we can see, it's better to look at the pictures first rather than just talk about it. So these are examples of open-ended and closed-ended manometers. So a manometer is different than a barometer, and that a manometer is used to measure the pressure of a gas that's in a container. A barometer is used to measure the pressure of the atmosphere. And so when we look at this on the far left, it's a closed-end manometer. So essentially you're thinking of the right-hand side of being just like a barometer, in that the gas, rather than atmospheric pressure, so the gas on the left is pushing the liquid up against gravity. And so you'll be able to measure the pressure of that gas directly. So the height that the column is, the density of the liquid, and the gravitational constant all those multiplied together will give you the pressure of the gas. And so when it's a closed-end one, that is your pressure of the gas. When it's an open-end manometer, you're measuring the pressure of the gas relative to the pressure of the atmosphere. So if you look at it, if the end is open on the right, atmospheric pressure is pushing on the right, the gas is pushing on the left, and you're going to see a difference in pressure. So if the arm connected to the gas is higher, that means the gas must have a lower pressure because it's not able to push the mercury down. If this, yeah, this is mercury. And so the pressure of the gas would be the pressure of the atmosphere minus that height. So that difference in pressure between the two times density times gravitational constant. Whereas the last picture on the right is the opposite situation where the gas has a higher pressure than the atmosphere because it's pushing the column up against the atmosphere to a higher height than the gas column is. And so the pressure of the gas is higher than atmospheric pressure. So the pressure of the gas in this situation would be the pressure of the atmosphere plus that difference in pressure, which is the height times the density times the gravitational constant. Yeah, so this is just an example where you work through, really it's a unit conversion. So it's closed end, therefore the 26.4 centimeters that it's moved is the pressure of the gas. And we need to convert that. Yeah, so those are just all examples, which I can work through in class. The ones that are already worked out in your book, you can go ahead and look through how they work out. But the bottom line here really is if it's closed end, 26.4 centimeters is the pressure of the gas, where if it's open-ended, the 13.7 centimeters is the difference in pressure. And so you have to think about adding it or subtracting it, whether the gas pressure is higher or lower. This just talks about how a stethoscope works. A stethoscope is measuring the pressure of your blood flowing through your veins. And so it's a similar idea to measuring gas pressure, but it's measuring the pressure of a liquid. And this is just showing us that a lot of our weather is created by differences in pressure in the atmosphere. So if you have a high pressure area next to a low pressure area, clearly you're going to have air moving from the high to the low, and that creates winds. So this is just showing you that the pressure of our air is very related to our weather conditions. This is a good diagram to think about in terms of the Earth's atmosphere. If you've already had global, what is it? Can't remember what the first class in EV is called, but some of you have taken a course on global atmosphere. So our atmosphere is separated into layers essentially. As you go up in the atmosphere, the temperature goes down and the density goes down. So the part of the atmosphere that we live in, the troposphere, is the lower 12 kilometers. This is where all of our weather happens. And then the stratosphere, that's where the ozone layer is. That's between 12 and 50 kilometers. And then we have 3 other regions of different types of density and temperature of air. So we want to now be able to relate pressure, volume, amount, and temperature into the ideal gas law so that we can relate those to each other and describe the state of a gas. So we're going to look at the mathematical relationships, which were all determined with experiments. And then we're going to use the ideal gas law and other gas laws to compute the various values of gas properties under specified conditions. So at constant temperature and pressure, a gas expands uniformly to fill the container in which it is contained. So that is how you think about what the volume of a gas is. As the definition of a gas is that it always fills its container, then that is the volume of the gas, whatever size container you have. So we're going to relate all of these. So there are lots of types of gases, and we're going to see that it's not going to really matter what type of gas. The ideal gas law is always going to be the same. So you have lots of individual elements that are gases. So in our atmosphere, we have mostly nitrogen and oxygen in the diatomic forms. Then we have very little H2, a little bit of helium, because as uranium breaks down in radioactive decay, we get helium and less argon. But you can also have compounds that are gases. So CO2, carbon monoxide, water, ammonia. There are lots and lots of compounds made of different elements that form gas particles. So all gases have the same dependence on these four properties. So that's the important thing. If we're calling a gas ideal, the volume, amount, temperature, and pressure are all going to be related with the ideal gas law. When we talk about amount, we mean number of particles. So we'll usually use the unit number of moles. So this is just talking more about why people were interested in study gases, mostly so that they could use balloons for travel. So if we look at the effect of temperature on gas pressure, if the hot plate's off, the pressure of the gas in the sphere is relatively low. But if you heat the gas, notice you're keeping the volume constant and the number of moles constant because the container is sealed. If you heat it, that means the gas is getting more energy and it's going to have faster and more collisions with the wall of the container. Therefore, the pressure is going to go up. So on the far left, we could say it's low pressure, depends on what the temperature is in the room, and it'll be high pressure as you raise the temperature more and more. So this pressure temperature dependence was figured out by two different people, Amonton and Gay-Lussac. And so you could call this law by either of their names. So the pressure of a gas is directly proportional to its temperature in Kelvin. So when you look at this, temperature goes up, pressure goes up. So they're directly related to each other. So that's only true, though, as I said, it's a constant volume. The container doesn't get bigger or smaller, and it's sealed, so the number of moles is constant. So that's only true at constant volume and number of moles. N is the number of moles. And so the way you could write that mathematically would be to say that P equals some proportionality constant times T. That would mean P goes up, T goes up, and it just depends on what that K, what that proportionality constant is. So this is just a graph showing you this situation, how if you measure pressure and temperature, you will see it as a straight line with a slope of K. So another relationship called Charles' law. So these are just different people doing experiments, looking at different properties of the gas and to try to see how they're related to each other. So the volume temperature relationship that Charles' law shows is that the volume of a gas is directly proportional to its temperature in K. And that would be if you keep pressure and number of moles constant. So volume goes up if temperature goes up, if you don't allow the pressure to change or the number of moles. And so this is just another graph showing that. So looks very similar to the pressure temperature relationship. Now that it's a K is a different proportionality constant. And so when a gas occupies a smaller volume, it exerts a higher pressure. When it occupies a larger volume, it exerts a lower pressure. And since P and V are inversely proportional, a graph of 1 over P versus V is linear. Okay, so they have moved on to the relationship between P and V. I'm kind of surprised they didn't say they were doing that. So we have the relationship between P and T, if V and N are constant. Then we have the relationship between V and T, if P and N are constant. And now we're going to look at T being held constant, but pressure and volume changing in relations to each other. So we have number of moles also constant. So we find that when you graph P versus V, it's a hyperbola, the top graph here. So it's a curved line. And so that's hard to do any sort of numerical fit like a least squares. And so we want to find something that we could graph that relates the two that should be a straight line. And it turns out if you graph 1 over P versus V, it should be a straight line. And so what that shows you is the volume of a gas is inversely proportional to its pressure. So pressure goes up, volume goes down. And that's only true at constant T and number of moles. And this is a law that was determined by Boyle. So V equals some constant over P. Same thing as saying when you graph 1 over P versus V, it has a straight line and the slope will be, what your K was. This is just showing you that in a little more detail. There's a discussion in the book on how your lungs work, but it makes sense if you lower the pressure in your lungs by expanding them, then gases are going to come in. And if you increase the pressure in your lungs by compressing them, you're going to force gases back out. So you can read through that in your book if you're more interested in how the lungs work to move air in and out. So the last one, Avogadro's law, is the volume of a gas is directly proportional to its amount. So you have more particles, you have a larger volume, and that's only true if you keep T and P constant. So these are the laws that were determined experimentally in 4 separate cases. So P equals KT, Gay-Lussac's, V equals KT, Charles, V equals K over P, Boyle's, and V equals KN, Avogadro's. I would never ask you the names of those individually experimentally determined laws, but I have heard that the MCAT will ask you questions like that, like whose law is this, which in my opinion isn't the important part of the law, but just to know that if you're thinking about taking the MCAT, there are a lot of things that you have to know versus understand. So when we take these 4 equations, we can combine them into a single law, and that law is the ideal gas law, which says PV equals nRT. So it's a relationship between all of those. So now you can say if all of them are changing, PV equals nRT is what I would use. The number of moles and R and T on the right-hand side. The R is called the ideal gas law, and it's really a combination of all those proportionality constants, and you can figure it out experimentally. So we'll look at that. So the 4 constants I just said are combined into a new one called R, and it's called the ideal gas constant. So the nice thing is not only is it true that you can combine these 4 laws and create the ideal gas law, but you can also work backwards. So it's really not necessary to remember these 4 relationships at the top, because you can take PV equals nRT and you can say, oh, what if I hold V and N constant? And you can derive a relationship that shows you how P and T change. And the same thing if you do V and T. So the ideal gas law, you can extract back out each of those individual laws that went into creating it. So when we look at this, pressure is, our P is the pressure in atmospheres. If we're using this gas constant, you can use other units for pressure, but you'd need a different unit for your gas constant. V is the volume in liters. N is the number of moles of the gas. T is the temperature, and temperature always has to be in Kelvin. R is the ideal gas constant. And so the gas constant of 0.08206 liters times atmospheres divided by mole times Kelvin is the one you would use if you're using this particular set of units for each of your individual properties. So we know now how to measure pressure. We can measure the pressure of the gas with a manometer. Volume, you've measured that many times. Number of moles, you could take the mass and then convert it to moles. Temperature in Kelvin with a thermometer, and then the ideal gas law is a constant. So the ideal gas law accurately describes the properties of an ideal gas. And what is an ideal gas? What assumptions are being made? That's the really important thing to think about. And now they go on to talk about you going up and down in water, and how the difference in pressure of the water will change the concentration of the gases. You can also read through that. I'm not going to go through it right now. And this is just showing you some of the things a scuba diver can see. And so I think we should finish that question there. What assumptions are being made about an ideal gas? So an ideal gas, as he said right here, maybe not. I thought he did. An ideal gas, the ideal gas equation can be used for any gas if you're at reasonable temperature and pressure. So what it's assuming are two big things. So if you have a big volume and you put some gas in it, if the gas particles are far apart, then they really don't take much that volume up. So one of the major assumptions is that the particles are so small and there are so few of them that the volume of the container doesn't change when you put them in, meaning the volume of the gas particles is insignificant. The other assumption is that the gas particles are far apart, they're whizzing past each other, but they don't hang around close to each other enough to interact in any way. So they're not attracted to each other, they're not repelled by each other. And so all they have is kinetic energy. They don't have any other kinds of interaction energy. We'll talk more about these assumptions when we talk about what it means to take into account another equation for a real gas. And so we'll look at those assumptions again. Okay, so standard temperature and pressure, just skip this. I find it very confusing. In our next chapter, we're going to have a different standard temperature. And so let's just, if I ever want you to calculate something, I will give you the temperature and pressure. I won't say at STP. So modified version of the ideal gas law. Moles are kept constant, but other properties change. I'm not sure why they say that that's modified. It's not what, they didn't mention that in the book. Okay, so regardless of its identity, 1 mole of gas behaving ideally occupies a volume of 22.4 liters at STP. I actually find if you remember that, you usually use it incorrectly. You usually use it when you're at a different temperature. So if you remember using that number from high school, feel free to do it, but just make sure you would only do that at 0 degrees. And I would prefer that you just calculate what the volume is if I give you a set of conditions and 1 mole of gas. So now, let me think. Yeah, we can continue. Let me just see. No, I think we'll take a break here. We're at least halfway through. And this isn't a new idea. All it is taking our ideas from understanding stoichiometry and how different quantities of reactants react together to make different quantities of products. And rather than thinking about starting with masses, think about starting with volumes and using the ideal gas law to figure out number of moles. So we'll come back to this after I take a break, and hopefully you take a break too.